Okay, so now in the previous video we derived Gauss's law. So we showed that integral E dot ds, right, over a closed surface was equal to Q upon epsilon naught, where Q was a single point charge inside the surface over which we are taking the over which we are evaluating this integral, right. So that was the one and simple basic case that we derived this for. Now I would like to derive this for any charge distribution. So before I go to that, I need to bring in one more concept. So let me do that. So we talked about the concept of solid angle, right? And now I want to push and get to one more point, which is the following. The question I want to answer is, let us say there is a closed surface, right? What is the angle subtended, solid angle subtended by this surface at a point outside the closed surface, right? If it's a point inside, right, then we know that the total solid angle is omega is equal to 4 pi, right? And we did that in one of the previous videos, right? So for a sphere it was pretty easy, and then we said for a non-spherical shape as well, right? It is going to be the same. Okay. Now what about this point which is outside, right? What will be the omega for this? Now let me give you the intuition and then I'll get to the answer. So let us say let's say there is some surface here, right? Let's say it's a part of a sphere, and you take this point, right? If I ask what is a solid angle subtended by this surface. So if in case it's spherical, then you'll say it will be this area upon r square, whatever that is, right? But now I'm saying more general case, need not be spherical, can be any shape, right? But there'll be some angle, let's call it delta omega, right? Now if I keep making it smaller and smaller, right? If I keep bringing these two lines closer and closer, right? Keep making the cone thinner, so to say. For a thinner cone, this will reduce. Now let us say if I take a thinner cone, which is like the following. So now here it is this line and this line, right? And the shape is no longer this, shape can be anything, right? In fact, it looks like an ice cream cone, right? Here, even though the cone is big, what will be the solid angles at this particular point for this surface? If you're looking for this surface, it is going to be same as this area, right? This area, if I can draw this whole thing, this area divided by r square, which is going to be this angle delta omega, right? As I bring as I make the cone thinner and thinner, this delta omega will become smaller and smaller, right? So I started with a broad cone. Now I'm making it thinner and thinner and thinner, right? The remaining surface stays. The surface is not becoming smaller, but the solid angle is becoming smaller and smaller. At an extreme case, let us say now I have shrunken it to a point where the two lines are now coming together. Now they're almost together. Now what happens? Now my delta omega tends to 0. Now when we actually close them, right? Now when we actually close them, what has happened? My delta omega now has actually become 0, and this point is now outside this surface, right? So this scenario is exactly the same as this scenario where you have a sphere, but your point is outside the surface. So for an outside point, right, the angle subtended is going to become 0. As you can see, the cone has become infinitesimally thin, then it becomes just a straight line, right? And therefore using this property that the solid angle subtended by a closed surface on a point outside is 0, right? Using that property, I am going to now later, right, in this video later, I'm going to prove that integral E dot ds, right, for a point outside the closed surface, for that point this is going to be equal to 0, right? This is going to come later, and this is one of the crucial requirements for the proof of Gauss's law. Okay. And now, based on these concepts, now let us try to prove the Gauss's law in general for any charge distribution. So let me state the problem. The general problem statement is as follows. So let us say there are there are a bunch of charges. Let us say there's one charge Q1, there's a charge Q2, and so on, right? Let's say up to charge Qn. And then there are further charges Qn plus 1, and so on up to, let us say, Qk. Okay. Now, I'm going to draw a Gaussian surface covering charges Q1 to Qn, but leaving out the charges Qn plus 1 to Qk, right? All these charges are left out. So there are some charges which are inside, some charges which are outside. Right? And I want to now evaluate, I want to find out what is integral E dot ds, right, for the closed surface where this is this green colored thing, this is my closed surface, right? So I want to evaluate this integral, right, over this closed surface. Now what does it mean? It means, conceptually what it means is, if I take small area elements at each point, I find the electric field and I take the area element vector and take the dot product, and then I add it up over this whole surface, right? Now what is the electric field here? E is the electric field due to all the charges put together, not just one charge, not just charges inside, but all Q1 to Qk, right? So now my electric field E, right, electric field vector is going to be E1, right, plus E2, right, and so on up to Ek, right, sorry, up to Ek. Let me actually break it down further. Let's say up to En, then plus En plus 1, right, and up to Ek. Now what are these electric fields? This E1 is the electric field because of Q1 charge standalone. Let's assume there was no other charge, right? Then the electric field at any point would be E1. E1 is the electric field caused by this one charge. E2 is the electric field because of charge Q2 and so on. Now I can write this, I can evaluate this as integral E dot ds, right, would be equal to integral E1 dot ds, right, dot ds plus integral E2 dot ds, right, and so on, right, up to integral En dot ds, right, plus then plus separately integral En plus 1, right, dot ds plus and so on up to integral Ek dot ds. Okay. So now, what is integral E1 dot ds? If this is just this is the value of the electric flux for the closed surface because of just one charge. And what is that? That was equal to, for just one charge inside the Gaussian surface, or inside this surface which we call a Gaussian surface, it was Q upon epsilon naught, right? So my E1 is going to be how much? E1 to En, right? So E1, integral E1 dot ds would be nothing but Q1 upon epsilon naught, right? And similarly we can do this up to Ek, integral, sorry, En dot ds, right, would be Qn upon epsilon naught, right? These are for all the charges inside, right? Now what about the charges outside? What about the integral values for this, for these terms, right? What will the value be? Right? Now what is integral En dot ds? This is nothing but the total electric flux. So just first thing we'll think a little intuitively, then we'll use this concept that we have derived here, right? So electric flux is the number of lines which are crossing the surface. If there's a charge inside, the lines because of this will be crossing the surface, right? And we can say there's a certain number of lines crossing, so a certain amount of electric flux. If I take a charge outside, let us say I'll take one charge here, right? So this charge will have electric field lines going like this, right? Going like this, and so on. Right? Now as you can see, these field lines will go in once and will go out once, right? From here also they enter once and they exit once. So the total number of lines crossing from the whole surface is going to be 0, because this is entering, this is exiting, they'll cancel each other, right? But a more mathematical treatment would be that for an external point, right? Here as we showed, for an external point, right, will show that integral E dot ds is going to be equal to 0. And how do I do that? I'll just do that here, right? Say integral E dot ds, right? This is equal to what? This is equal to, let's just take one charge, let's say Qn plus 1, right? So En plus 1, what will this be? This would be integral. What is En plus 1? So electric field is going to be nothing but 1 upon 4 pi epsilon naught, or let's say kq upon r square, right? So this would be 1 upon 4 pi epsilon naught into Qn plus 1. So we'll write this as Qn plus 1, right? And this would be this into this ds, right? ds cos theta, right, upon r square. And what is this? So just take the charge and 4 pi epsilon outside because they're constant. This would be sorry, let me first take the constant outside. This would be Qn plus 1 upon 4 pi epsilon naught, right? And again ds, so this would be an integral of that, and ds cos theta, right, divided by r square. What is ds cos theta r square? This is nothing but this is my d omega, right? So this is going to be integral, right? Sorry, this would be q n plus 1 upon 4 pi epsilon naught, right, into d omega, right? D omega over a closed surface, and here my charge is outside, right? So we just showed that for an outside charge, right, the total angle subtended is going to be, solid angle subtended is going to be 0. So this is going to become 0, right? And therefore this whole thing is 0. So which means E dot ds for a charge outside is going to be 0. The same thing that we showed using electric field lines, right? So now I can write that this whole thing, right, this whole term, right, can be written as integral E dot ds, right, is equal to q1 upon epsilon naught plus q2 upon epsilon naught and so on up to qn upon epsilon naught, and I can take 1 upon epsilon naught common, then I can write this as q1 plus q2 and so on up to qn, right? And for qn plus 1, for these things we have shown that each of them is going to be equal to 0, and so this is nothing but, what is this? This is the charge inside. So this is going to be q inside upon epsilon naught, right? So this is the proof of the final proof of my Gauss's law. So I'll write it somewhere here so we can see that. So we have shown that integral E dot ds, right, is equal to q inside upon epsilon naught. This is the complete Gauss's law, and this is the most generic derivation of the same. Thank you.